Alright, this is the start of Unit 7, Similarity, with Day 1, Similar Polygons. I am going to go over the warm-up for this lesson because it does tie into what we're talking about. First of all, whenever you see a similarity ratio comparing two things, this is one way that you could use that. Since the ratio of the lengths of the two pieces is 7 to 4, and the original was 33 inches, I know that 7 parts, and I'm going to use an X to represent parts. 7 parts plus 4 parts equals 33 inches. And so now I can actually figure out how big a part is by combining like terms, dividing by 11, that X equals 3. So each part is 3 inches long. Now I can tell what the lengths of the two pieces of wood are. That 7 times 3 would be 21 inches for the longer piece, and 4 times 3 would be 12 inches for the shorter piece, and that makes it 33 inches and does maintain the ratio. On the second warm-up problem, I have a rational equation. We are going to be getting more into this in Math 3 with rational equations, but for this one it's actually pretty straightforward because all it has to do is really cross-multiply. That you're multiplying by 8 on both sides to cancel this out, and you're multiplying by 4 on both sides to cancel this out. So let's go ahead and do that. That 8 will now be multiplying 2x minus 1, and the 4 will now be multiplying x plus 4. When I multiplied by the 4, it canceled this one out. When I multiplied by the 8, it canceled this one out. Now we can simplify this stuff down, distributing the 8 and distributing the 4. And we can now actually combine like terms by maybe minusing the 4x. So 12x minus 8 is equal to 16. Add the 8 over. 12x is equal to 24. Divide by 12x is equal to 2. And that does match up what you would want to check your answer in these situations. But that does actually work out in this equation. And I know there are a couple different ways that this could have been done, but just getting you a quick cross-multiplying problem because that's what we're going to be using with similar figures. Here's some notes about similar polygons. Talking about polygon quadrilateral ABCD is similar to WXYZ. What that means is by the definition of similar polygons that angle A and angle W would have to be congruent. So your corresponding angles of similar figures are congruent. That's what this is saying. Corresponding angles are congruent. Corresponding sides are not congruent though, but they are proportional, which is what this says. And you can see that written right up here, that 15 to 5 is 3, 12 to 4 is 3, 21 to 7 is 3, and 18 to 6 is 3. So all the sides reduce to 3 to 1. So how would you write this out? This is an example of a similarity statement. The ABCD is similar to WXYZ. See that this does not have an equal sign on it because they are not congruent. They are simply similar. The similarity ratio is 3 to 1. This is something you usually will list with that if you're able to. So this is how a statement will look for similar figures. So this is relating back to what we did on the last unit where we named corresponding parts of congruent triangles. Well, here we're having corresponding parts of similar triangles. Now, the angles that are congruent would be that angle A is congruent to angle R. Hopefully this feels familiar. The angle B would have to be congruent to angle S, and that angle C is congruent to angle T. Now, the sides are not congruent for similar figures. We're going to write a proportion that relates to corresponding sides. So a pair of corresponding sides is AB to RS. Needs to equal BC to ST. Using this statement up here, I'm getting BC matched ST. And that AC equals RT over RT. ACE equals AC over RT. And there's my proportion for this statement. Looking at some of the notations is the reason why I showed this problem. With this one, you have the triangles are similar. Which of the following similarity statements is not true? This means corresponding. So does HK correspond to QR? Indeed it does. This ratio does work out since the corresponding parts match, that GH corresponds to PQ, first and second, that GK corresponds to PR. Now, you need to make sure that it's going in the same direction. Like if this was GH over PQ equals PR over GK, that would all of a sudden not be true because they didn't follow the order that the first ratio was. Now, if both of them were flipped, that would be fine. So, for instance, if PQ over GH equaled PR over GK, this would be fine as a separate statement. That checks out because they're still both flipped. Still true. The angle K does correspond with angle R, so that's fine. But angle GHK, which would be angle H here, does not correspond to angle QPR, P being the first letter. So that's actually the one that's not true. All right, going to have to do some assumptions on example 3. As we're looking at these, we are going to be able to safely assume that these are rectangles. So all my angles are matching. Angle A does match angle F, and so on, because they're all 90 degrees. Now we need to see if the corresponding sides are actually similar. So with this being a rectangle, I actually only have to make one comparison. Let's do short side to short side, so 10 to 12. And compare that with long side to long side, 12 to 14. And see if these are actually equal proportions. So 10 twelfths reduces to 5 over 6. 12 over 14 reduces to 6 over 7. Since those do not reduce down to the same ratio, these figures are not similar. An explanation could be as simple as that AB over FG did not equal AD over FH. And that wraps up this one. Now here's an example of what it would look like probably when it does work out. Okay, so we're going to make the same comparison that we did, short side to short side, so 10 to 8. And long side to long side, 12 to 9.6, and see what they reduce down to. So your short side doesn't have to be the numerator like it was on the last one. It can be like this. So 10 over 8 reduces to 5/4. And now we got to see what 12 over 9.6 reduces to. Personally, what I do is I actually get rid of the decimal. So I would actually multiply the top and bottom by 5 in order to get this to 60 over 48. Much easier to deal with. Now I can divide 12 out of both of those, and I get 5 over 4. So they do match. Everything checked out here. Now I'm going to show you how to write a similarity statement. In this case, ABCD is similar to RSTU, making sure that the corresponding sides matched up, AB and RS, and AD and RU. Now, I also need to state the similarity ratio with a similarity ratio of 5 to 4. Now, what happens is, if I had listed RSTU first, if I had said RSTU is similar to ABCD, the similarity ratio would then be 4 to 5. It would actually flip it. This problem wants you to write a similarity statement. So I would simply say that A, B, C, D, E is similar to, now make sure that the parts match, that R will match to A, S does match to B, and then we work our way around T, U, V. Now it wants us to find X and Y. Also, I needed a similarity ratio. And to do that, I'll refer to the sides that they actually gave us information as 6 to 4, which is 3/2. All right, now I'm going to use that similarity ratio to calculate X and Y. Starting with X here, X is on the first figure, so X, which is DC, will match to, let's refer to our statement, DC matches to TU, which is 3. So X to 3 is equal to our similarity ratio that we came up with, 3 to 2. Cross multiply, 2x equals 9, and divide by 2, x is equal to 4.5. To do y, it's a similar process, but if I do y plus 1 over 8, that's going to flip this to 2 over 3 whenever I write it down. I'm actually just going to leave it as 8 to y plus 1. Needs to match my proportion of 3 to 2 from my figures. Making sure that I'm going from the bigger figure over the smaller figure, because that's how I set this up at the beginning. As long as you're consistent, you'll be fine. Cross multiplying, I'll get 16 is equal to, when I distribute the 3 to the y plus 1, I get 3y plus 3. Subtracting 3 over, I get 13 equals 3y, and dividing by 3, I get y is equal to 13 thirds. Which could be 4 1/3 if you'd rather write it like that. And we're done. So for perimeters, we're close to wrapping up here. For perimeters, you're going to see that they are actually proportional, just like the sides were proportional. And that's because perimeter is one-dimensional. You don't say perimeter is to the foot square, you just say perimeter is to the nearest foot or unit, whatever that unit may be. So perimeter follows the same rule as far as your proportions go. So for an example like this, really I'm just going to start filling in information on one of them, and I was told that they were similar. So let's maybe move the 7 over to RV because it said those were congruent to 10.5 over. And now I can just do a little bit of work to calculate ST here. It did want me to find the scale factor first of ABCDE to RSTUV. Now that's smaller to bigger, so I would say that is 4 to 7. This answers the first thing that the problem wanted us to do. Now it wants the perimeter of each figure. To do that, I'm actually going to go to this larger one since I have more filled in about it and calculate ST really quick using this similarity ratio that I just came up with. So 6 to ST is equal to 4 to 7. So now I'll cross multiply that. 4 times ST is equal to 6 times 7, which is 42. And now I'll divide by 4 on both sides to get that ST is equal to 10.5. So the perimeter of RSTUV is equal to just adding those 5 sides together. And that comes out to 45.5. Now some of you might be jumping over here and filling in information that this is 4, that this would have to be 6, this is 6, and this is 6, and adding all those sides together. I'm actually going to go a little bit of a different route because I'm going to use what we just talked about as far as perimeters go, that perimeters also follow the similarity ratio. So in this case, the smaller perimeter that we don't know, I'm going to call it P, is going over the larger perimeter, 45.5, is going to equal 4 to 7. The similarity ratio is where that came from. Sometimes this is actually really useful as you don't have quite all the information on one of them, and so you're having to rely on this, that the perimeters will follow the same similarity ratio. Some of y'all might be really wanting to cross multiply here and make it 7p equals 4 times 45.5, but remember, go maybe the easiest route, that we only have to multiply 45.5 on both sides to solve for p. So this actually takes a little bit less work if you keep that in mind. When I do that, I get 26 for the smaller perimeter. So the perimeter of the smaller object is 26 units, which is what you would have gotten filling in the missing sides. But like I said, sometimes the way they frame up a problem, you have to rely on your knowledge that the perimeters are going to follow the same similarity ratio. And I know we've looked at a lot of examples, but this is our very last one. We're going to compare areas. Now areas do follow a different rule, and what that rule is that if the similarity ratio of the lengths of two polygons is a to b, then the ratio of their areas is a squared to b squared, because you're talking about square units here. So keep that in mind. Now that we know that the area of the larger one is 56 square units, it says, so I'm going to write that in, area equals 56. I'm actually going to be able to work off of that and figure out the area of the smaller one. All right, let's go ahead and call this area down here the area that we don't know. And let's make our comparison. First of all, let's figure out a similarity ratio. I'm going to use 8 to 6, which is 4/3. So the larger figure to the smaller figure is 4/3. But I'm not going to use 4/3 when I start calculating area. Remember the note said I have to square both of them to know how the areas compare. So I'm actually going to use 16 to 9 as my similarity ratio for my areas. And I'll set that equal to 56, the larger area that I know, over the smaller area that I don't know. And now I will cross multiply that. 16a is equal to 9 times 56, which is 504. And divide by 16, I get 31.5 for my smaller area. So whenever you have a similarity ratio and you're wanting to compare areas, you've got to square that similarity ratio. And very lastly, for polyhedrons, if the lengths had a ratio of A to B, for similar polyhedrons, they would be able to compare with A cubed to B cubed for their volumes. Now their surface areas would still be A squared to B squared, but their volume, since those are cubic units, is A cubed to B cubed. All right, that wraps up today. Please let me know if you got any questions. Thank you.